Hi, welcome to es301 Engineering Analysis. This is chapter 9 on Gauss elimination. So here are the learning goals. At the end of this video, you'll understand how systems of equations can be represented in a matrix form. You'll know how to solve two simultaneous equations graphically. You'll understand when systems have no solution. You'll be able to use Cramer's rule to solve a system of equations. You'll know how to implement Gauss elimination in order to solve a matrix of equations. And you'll understand how pivoting can reduce round-off error and how to implement partial or complete pivoting in order to help minimize that. So first, I just want to kind of look at two simultaneous equations. So here we have two equations. We have two variables, x1 and x2. And anytime you have the same number of equations as unknowns, you could go ahead and solve this. And there's a couple different ways you could solve it. We could go ahead and take maybe the bottom equation first, go ahead and solve for x1, and then plug that into the top equation. Another way to do that is you could do it graphically. You could just graph what each of these equations are, where now I've got this axis over here is x1, this is x2, and so this right over here is the plot of this top equation. This right over here is the plot of the bottom equation. And then what we can realize is where they intersect would be the solution. And so here they intersect at a value of x1 is equal to 4 and x2 is equal to 3. So that's the solution there. So there would be kind of a graphical way to go ahead and solve two equations to go ahead and find out what the solution is. There's a couple of pitfalls that you need to be aware of. Is that, as I said, anytime you have two equations and two unknowns, you can solve that for a single solution. There's times when there's not a solution, and they're called singular equations. Or singular systems. And one is if your equations the lines are parallel, which means effectively you just went ahead and added a constant to one of these equations. And so if you look at what these two equations right over here, all that happened is the only thing that changes is this intercept value is 1.5. And so effectively this equation here, if you add a half to it, became this one. We just shifted this equation up. And so that's not going to have a solution. You end up with parallel lines. Right over here, we have effectively the same line, and what that means is you just went ahead and took one equation and multiplied by a value to get the second equation. So if you look, what happens if I take that top equation and multiply it by 2, I end up with the bottom equation. Minus 1/2 times 2 is minus 1. 1 times 2 is 2, and so you end up with the same line. It's an important point because we're going to come back to that with Gauss elimination, is that if you go ahead and just multiply or divide through by a constant, you end up with the exact same line or the exact same equation. Another pitfall, there's a solution here, but you realize that if your lines are nearly parallel, any little small change in one variable ends up with a pretty dramatic change in the other one. And so you realize is that a very small change in x2 ends up with a very large change in x1. And so if I'm not able to represent numerically one of these values very accurately, due to round-off error, I can end up with large changes down here. And we'll see that when we talk about pivoting here in a little bit. So now if we were to go ahead and just increase the number of equations and number of unknowns, what I have now is three simultaneous equations, x1, x2, and x3. And again, three equations and three unknowns. And as long as they're not parallel to each other or the same line, which none of these are, there's going to be a solution to it. But now I'm not going to have an intersection of lines. What effectively each one of these are is a description of a plane. Because you realize, for example, if I look at this top equation, if I rearrange it, I could say that x3 is equal to 18 minus 3x1 minus 2x2. And what that tells me is that for every value of x3, for every pair of values of x1 and x2, calculate a value of x3. So what that is that's the description of a plane. And so each one of these is three planes. And so if I was to go ahead and plot those three planes, and here I've plotted it in MATLAB, so instead of lines now I have planes, there's going to be a single point where those three planes intersect, which is this point right there. And that's going to end up being the solution to this system of equations. So it's not quite as easy to do graphically, but it can be done. If that image isn't real obvious, here I have a little video I just recorded where I'm just kind of rotating through the axes in MATLAB. And so you can kind of tell where there's three planes intersect, and I've drawn a red dot where there is the solution to that system of three equations. Now I want to talk about matrix representation of these equations, because what we end up having in numerical systems is not 2 or 3 equations, but often hundreds or thousands of equations. And so we'd like to be able to start representing those in a little bit more compact form. So if I was to go ahead and take these equations right here, these 3 equations, I could write them in a matrix form, which would look like this. So I've taken the coefficients from the left-hand side here. That's usually called my A matrix, or represented with little values A. And I put them over here. So 3, 2, and 1 is my 3, 2, and 1, which are the coefficients at the top. And then I take the right-hand side, the constants, and I put that over onto the other thing over here as a vector here, and that's often called my B vector. And so this represents the same as these equations, because I would take 3 multiplied by x1, 2 times x2, 1 times x3 is equal to 18, and that's that equation is right there. It's just a little bit more compact form. And so what I would like to do now is be able to find a way to go ahead and solve this system of equations to go ahead and find out the solution. And the solution right now turns out that this value of x is 4, 3, 1. x1 is 4, x2 is 3, and x3 would be equal to 0. All right. Now it's fairly simple in MATLAB. Let's go ahead and say that that matrix is A over there, and this is B. I could go ahead and say A/B in MATLAB, and it'll actually end up giving me the solution of x, which is equal to 4, 3, and 0. But what we're going to do is look how to numerically implement what MATLAB is doing inside there. So we'll look a couple different ways. We'll talk about Cramer's rule first. And so let me just go ahead and review what is a determinant of a matrix, if you don't remember or haven't run into a determinant before. If I have a 2 by 2 matrix, for example, let's just look at the lower right-hand side. The determinant is here, it would be 2 times 2 minus negative 1 times 4. And then as the matrix gets larger, what I'm going to do is I'm going to take my value of 3 and multiply it by the determinant in the lower right-hand corner. Okay? So, for example, if we were to go ahead and just look at that again, let's determine the determinant of this whole matrix. I'm going to take 3, which is this value up here in the upper left, and then I'm going to go ahead and multiply that by the determinant, which would be 2 times 2, and then I'm going to subtract minus 1 times minus 4, or I'll just do 1 times 4, let those two minuses cancel out. So there's my first term, and I'm going to keep adding that. So I'm going to add this to 2, that's my middle one over here, and now I'm going to have the determinant, and usually what you do is you go ahead and just kind of repeat these values. So I'm going to have a minus 1, and a 3, and so I'm going to look at those two values right there. So what I end up having is minus 1 times 3, and then I'm going to subtract, and then it's a minus 1 times 2, minus 1 times 2. All right, and then I'm going to add my last one, which is 1, so it's that coefficient 1, and my determinant there, minus 1 times minus 4, I'll just call that 1 times 4, cancel out those, and then minus 2 times 3, so minus 2 times 3. And now I'm just going to go ahead and do all of that algebra, and if I go ahead and finish that out, what I find out that that whole value is equal to minus 4. Right? So that's the determinant of this matrix, and you want to practice that. MATLAB will go ahead and give it to you. There's a function called det, which will give you the determinant. So if that was my A matrix there, if you do det of A, it should go ahead and tell you that that's equal to minus 4. Now the reason we read that is there's something called Cramer's rule, which you may have run into before, which tells you can go ahead and solve for these variables x1, x2, x3, etc. Using a bunch of determinants. And what you do, if the determinant of the matrix A is called capital D, and then I take another determinant, we have these vertical lines, this is just a symbol of the determinant, and what I'm going to do now is to find x1, I'm going to take the first column of values and replace it with B. And so what I'm going to do is I'm going to put 18, 2, and 0 in there, and then I'll go ahead and leave those two columns the same. And then find that determinant and this one right over here, and then that'll give me my value of x1. And you might want to verify that you can do that or look in the example. What that comes out to be is minus 16 when I replace the b's over here. We saw the determinant of the matrix A was minus 4, and so that's going to give me equal to 4, and that is actually what the value of x1 is. And then you can do that again for x2 and x3. So this is a way to do it. It obviously involves a lot of calculations because you're finding lots and lots of determinants. You have to find it for every one of these values plus the A. So if you had 100 variables, you'd end up having to find 101 determinants. And if you had 100 variables, you'd have a 100 by 100 matrix. You could realize that finding those determinants could be a little onerous. So we'd like to find an easier way to do that. And so what we're going to do now is we're going to talk about Gauss elimination, which is another way to do it. It involves less calculations in there. So let's just come back. Here's my system of equations I want to solve. And I want to find my values of x1, x2, and x3. And what would be nice is if that matrix had a bunch of zeros in it. In fact, if it had a bunch of zeros in the lower left-hand corner. The reason is, then I could solve the bottom one, because that's only got one equation. That says 2 times x3 is equal to 0. I solve that. I find out that x3 is equal to 0. And then I can go up to the next equation. I already know what x3 is, and now I've got 2 times x2 minus 1 times x3, which I already found is equal to 2. I can quickly find x2 and then keep going up. So that's called back substitution. So if only my matrix had zeros in this lower left-hand corner, I could do that. And we can go ahead and make our matrix have this by multiplying some of these equations by some factor and then doing some arithmetic on them. Remember, this is effectively just anytime I multiply or divide, I'm ending up with the same line. And so what we're going to do, for example, is I'm going to go ahead and do a bunch of arithmetic such that I can get zeros in the lower left-hand corner. Okay, so let's go ahead and do that. And so I'm going to go ahead and look at the first step. So what we want to do is we're going to start off with this value here. And I want to make that a 0. And the way I can do a 0 is by using this top equation. So I'm just going to leave the top equation alone. We'll call it 3, 2, 1, and then 18. But what I'm going to do is I'm going to take that top equation, multiply it by a third. So I'll multiply it by a third. All right. And then just go ahead and add the 2. And so if I have that top equation multiplied by a third and add it here, I'm going to end up with a 0. So if I do that, I'd have a 0 there. And then what I have to do is with the remaining ones. So I multiply the whole thing by a third. So what I end up having this top equation is I have 2 thirds. All right, and so I'm going to add that. So I'm adding my 2 thirds to 2. And so that would end up giving me a factor of 8 thirds there minus 2 thirds there and 8 there. And then I am going to do the same thing down here to make a 0. And now I'm just going to be subtracting the top equation from the bottom one. So now I'm just multiplying it by 1 and then subtracting it. And that's going to give me a 0 and a minus 6, a 1, and a minus 18. Now I realize I got my zeros all in the first column there. So now I'm just going to do one more step where I want to get the 0 right down here. I want to turn that value there to a 0. So let's just go ahead and write down our values that we had, 3, 2, 1, 18. This one, middle row, is not going to change, so that's going to be 0, 8 thirds, minus 2 thirds, and 8. And now what I need to do is I need to go ahead and get rid of that 6. And so I realize what I'm going to do is I'm going to multiply by 6 over 8 thirds, and then just go ahead and add it, because there's a negative sign there. And so if I do that, I'm going to have a 0 there and a 0 there. What's going to remain here is a minus 1/2, and that's actually going to be 0. And so now if I come back to what this is, I realize now I've got my matrix where I've just got numbers in the upper right hand side, right? Minus 1/2 of x3 is equal to 0 gives me x3 is equal to 0, and I can continue on. So that's called Gauss elimination, and that's one way you can go ahead and solve these, and requires a little bit less calculation than Cramer's rule. But there's kind of a danger you can run into if you just do that naively, and that's called naive Gauss elimination if you do it the way I showed. And that comes when you have matrices that have some really small numbers and some really large numbers in it. And let me mention where this comes up, because this actually happens a lot. And what we'll see in our next video is that a lot of times these systems of equations come, for example, so say I'm just trying to go ahead and solve for the temperature distribution in some sort of plate where I have all of these points inside here, if I'm using a finite difference or finite element method. And if I'm trying to find a value there, maybe that's like x21, what I'd find out is that it's fairly strongly influenced by values close to it. It has really small influence from points really far away. And these points right over here can represent points really far away. So what I would want to do is go ahead I need to be careful when I have matrices like that. And so this is an example. These numbers are actually from the textbook. And I'll show you what, just kind of step through quickly, and you can look at this as well. If I was to go ahead and just do naive Gauss elimination, I got to take this top equation, and what I need to do is divide by 0.0003, or effectively I need to go ahead and multiply it by 3.33, etc., etc. And then I need to go ahead and subtract that from this equation. And if you were to go ahead and do that step, here would be your next equation, and since you multiplied this equation by a fairly large number, now I've got this minus 9999 and minus 6666. And now if I go ahead and finish this out, well, this is pretty simple. x2, let's go ahead and solve for that. What I have is my 6666 over 9999, or effectively 2 thirds. But when I do my next step, where I have this small factor for x1, it comes out to be 2.001, and then minus 3 times 2/3, and that's all over 0.0003. Right? Now, notice that 3 times 2/3, well, that's almost 2, and this is almost 2 as well. And so I'm taking two numbers that are really close. I got a really small number divided by a really small number, and if I'm not representing this very well, I end up with some round-off error. And so what you'll see, in the book shows you an example that as you get more and more digits of precision in here, you actually get different values, and so you're susceptible to round-off error. And so what we're going to look at is a way to eliminate that. And the way we eliminate it is we just don't have small values on the diagonal, and that's called pivoting. Right? And so with pivoting, what I do is let's just take an equation or a matrix of equations that I have here. And what I want to do is I want to go ahead and make my largest values be on the diagonal. Right? So if I look at this, what I'm going to do is I'm going to start at 1, this first column, and look down, find the largest factor, and move that equation there. So I'm going to move this equation up to the top. Right? And then I'm going to go ahead and look at the remaining ones and figure out what's left. Okay, so I've already moved this 8 equation up there, but now I've got this equation, this one, and left. And now I'm going to move the one with the 12 up to there. Right? And then what I'm going to have left is I've got this equation, my 1, 2, 9 equation, and then my other one. And so that's what's going to be left, is I'm going to go ahead and use this equation right over here, third, and then that's going to go ahead and leave that one there as my fourth equation. So all I'm doing is rearranging the order of the equations, and so what this is going to end up with is 8, 1, 5. What did I have? 8, 1, 5 minus 2 minus 2. That's this equation moving to the top. My next one right over here is going to be my 1, 12 minus 3, 9, and 12. So that's that one right there, and this one right over here. And so of the two that are left, I realize 9 is the largest, so I'm going to go 1, 2, 9 minus 2, 4. And then the only one that's going to be left now is going to be my 2, 7 minus 2, 4, and 1. And what you do, if you look down at your diagonals now, the number, there's always going to be, everything below it's going to be smaller. This is called partial pivoting, and this is usually good enough to go ahead and eliminate some round-off error. The other thing you can do is you can go ahead and rearrange columns to go ahead and further make sure that your largest factors are in here. So what I would do is look down to the right-hand side and realize if I want to move some of these columns over. That's not normally done. It adds a lot of complications and doesn't further reduce the error all that much. So usually we just stop at partial pivoting, which means all we're doing is rearranging the rows and we don't bother rearranging the columns. Alright, so let's review what we talked about in this video. What we saw is that simultaneous equations can be solved graphically, but only for kind of low-order systems, 2 or 3-order systems. And then it's really hard to do graphically because we really can't see in 4 and 5 dimensions very well. We saw that systems of equations with no solution, they're called singular matrices, meaning that there's no solution to them, and they're analogous to parallel lines in 2 dimensions or parallel planes in 3 dimensions. We saw Cramer's rules, one method to solve a system of equations, but it requires lots of intermediate calculations. We have to calculate lots and lots of determinants. A more efficient way would be Gauss elimination. It's more straightforward. It's quick. Naive Gauss elimination is susceptible to round-off error. Round-off error occurs when I have small factors in the diagonal, and so I can go ahead and eliminate that or minimize it because pivoting helps reduce that potential round-off error, which involves rearranging the rows so that my largest values are on the diagonal.